Hello everyone, welcome to Chem 9. Today we will begin chapter number 9. In this chapter we will learn about acids and bases. We will also learn about their properties and their reactions. And this chapter also includes buffers. This chapter is divided into 4 sections. In first section we will learn about definitions of acids and bases, and we will also learn about their properties. Then we will discuss about a parameter called pH. pH tells us about the strength of any acid or a base. And in third section, we will learn about various reactions of acids and bases. And finally, we will discuss about buffers. We are familiar with many foods that contain acids. For example, all citrus fruits such as oranges, lemons, limes, they all contain citric acid. That's why they are known as citrus fruits. Similarly, vinegar contains acetic acid, and carbonated beverages, they contain dissolved carbonic acid. The common theme in all these foods which contain acid is that they taste sour. They have tart taste. Similarly, there are many foods which contain bases. For example, chocolate is one of the food which contains base. The common property between all bases is that they all taste bitter. So all bases are bitter and all acids they taste sour. So now we know the difference between the taste of acids and bases, but how do we define them chemically? So the first definition of acids and bases was given by a Swedish chemist. His name was Arrhenius. That's why this definition is known as Arrhenius definition. Arrhenius defined that acids are those substances which produce hydronium ions when they are dissolved in water. Hydronium ion is formed when the H positive from any acid mixes with water. So this combination gives us hydronium ion. So for example, an equation of HCl and water is given here. So as you can see that the H positive ion from hydrochloric acid combines with water and we get hydronium ion. So any substance which gives hydronium ion when mixed with water is known as an acid. So this is the definition given by Arrhenius. So therefore hydrochloric, this HCl, the name is hydrochloric acid because it's an acid, because when it mixed with water gives hydronium ion. On the other hand, Arrhenius defined that bases are those substances which produce hydroxide ion in water. So for example, sodium hydroxide, when mixed with water, it gave rise to hydroxide ion. So therefore, sodium hydroxide is a base. So these are the definitions of acids and bases given by Arrhenius. So that's why these definitions are known as Arrhenius definitions. In previous chapter, we learned that ionic compounds are electrolytes. By electrolytes, we mean that when we dissolve ionic compounds in water, they will conduct electricity throughout the water. For example, NaCl is an ionic compound and it is also an electrolyte. Now, if our ionic compounds contain hydroxide ion, then all of those ionic compounds are bases. For example, sodium, instead of a chloride ion, if it's bonded with hydroxide, so sodium hydroxide will be a base. So all group 1A hydroxide salts and group 2A hydroxide salts are bases. So therefore group 1A contains lithium, sodium, potassium, rubidium, cesium. So all of their hydroxides such as sodium hydroxide, potassium hydroxide, rubidium hydroxide, cesium hydroxide, they will all be bases. They will also be electrolytes because they are still ionic compounds, but on top of that, they will also be classified as bases. Similarly, group 2A hydroxides such as calcium hydroxide and magnesium hydroxides, they are also bases. Remember, because they are ionic compounds, that's why they are also electrolytes. So we can say that all ionic bases are also electrolytes. Group 1A hydroxide salts are freely soluble in water. They are strong electrolytes and they dissolve entirely to produce ions in water. For example, if we dissolve sodium hydroxide in water, if we take solid sodium hydroxide, it will completely dissolve and it will dissociate to produce ions, and these are called aqueous ions because they are soluble uh, in water. On the other hand, group 2A hydroxides, they are slightly soluble, so partially soluble in water, and they are weak electrolytes and they dissolve slightly to produce few ions. So for example, if we take calcium hydroxide, some of this calcium hydroxide will dissolve and some of it. So we will get few calcium ions and few hydroxide ions in the aqueous solution, but remaining will be the solid calcium hydroxide. So that's why the reversible arrow. That means that some of them dissociate to give us iron, but majority of them go back and give us a solid calcium hydroxide. So that reversible arrow indicates that's a weak electrolyte, and or it's a dissociation is not 100%. Okay, so let's identify which of these following ionic compound is a base, and we have to explain. Remember, according to Arrhenius definition, any substance which produces hydroxide ion in water will be a base. So it means for an ionic compound to contain to be a base, it should contain hydroxide, right? So in this list, we see compound A containing hydroxide and compound C containing hydroxide. So these two are the bases. Others are not. And the reason is that they contain hydroxide. So when they will be dissolved in water, they will produce hydroxide. So hence they will be bases. Arrhenius theory works well to define majority of acids and bases. However, there are certain compounds which do not fit according to the definitions proposed by Arrhenius. For example, ammonia. Ammonia, as we know, is a base. According to Arrhenius definition, bases should release or produce hydroxide ion in water. But as you can see, there is no hydroxide ion. So therefore, how can this be a base? So according to Arrhenius theory, this compound should not be a base, but we know for the fact that it is a base. So in order to accommodate these kind of compounds, a new approach or new theory was proposed by two chemists named Bronsted and Lowry. So therefore, this theory is known as Bronsted and Lowry theory of acids and bases. This theory is based on acceptance or donation of H positive ions. And these guys called H positive ion as a proton. So H positive ion is a proton. Let me explain why H positive is called a proton. If we take a look at a neutral hydrogen atom, so hydrogen atom has one proton and one electron around it. So this is the structure of hydrogen atom. So if hydrogen atom goes from atom to H positive, so it means it needs to lose an electron. So if it loses an electron, what is left with? It left with only the protons. Therefore, H positive is known as a proton because it is nothing, just a proton. So now we know that H positive is proton. So let's take a look at what Bronsted and Lowry said. So according to this theory, an acid is a substance which donates a proton it's not actually donating the proton, it donates H positive ion. So although we call it a proton, but understand it that it is a H positive ion. And according to Bronsted and Lowry theory, a base is a substance which accepts a proton. So for example, let's take a look at it. In this example, hydrochloric acid is combining with water and it is giving us hydronium ion and a chloride ion. But if we look closely, you will see that uh, hydrochloric acid actually is giving away its H positive. So H positive is being donated to water. So therefore, hydrochloric acid is a H positive donor because it's donating it. And after donation, that's a leftover part, right? So because HCl is donating it, so therefore HCl is an acid. Now, if HCl is donating it, then our water molecule that is accepting the H positive. And we know that according to definition, a base is a substance which accepts, so therefore water is a base. So that's how Bronsted and Lowry theory explains what are acids and what are bases. Now initially I told that ammonia is a base, but Arrhenius theory does not explain why it's a base. So let's see if Bronsted and Lowry theory is any better. So let's take a look at reaction of ammonia with water. In this case, after reacting with water, ammonia becomes ammonium ion and water becomes hydroxide ion. So what actually happened? In this case, if we take a closer look, we'll see that the H positive goes from water to ammonia. So therefore, water is a H positive donor or proton donor, and we know anything which donates a proton is an acid. So therefore, water is an acid. But we are more interested about ammonia. So ammonia, what happened to ammonia? Ammonia has NH3 here, but on this side it is NH4, right? So that means that it got one extra proton from somewhere, and now we know that extra proton came from, or extra H positive came from water. So ammonia is a H positive acceptor. And we know any substance which accepts a proton is a base. So therefore, according to Bronsted and Lowry theory, ammonia is a base. So hence this theory explains why ammonia is a base. Another interesting thing I would like you to notice here is the character of water. It is unique. In the first reaction, if you see, water is accepting the proton and water is a base. But in the second reaction, water molecule is donating the proton, therefore water is acid. So what's happening with water? Is it an acid or a base? The answer is both. Water is a special kind of a molecule. So there are few other molecules also which can behave the same way, but let's focus only on water. So water is a substance that which can act as an acid in certain reactions, or it can also act as a base in some other reactions. So these kind of substances are known as amphoteric substances. So as we saw, water is a special kind of a molecule. So according to Bronsted and Lowry theory, water can accept a proton or it can also donate a proton. So therefore it can act as acid or a base. So any substance that can act as an acid or a base is known as amphoteric substance or amphoteric compound. So water is a amphoteric compound. So as we learned that according to Bronsted and Lowry theory, any substance which donates a proton will be classified as an acid. So let's write an equation for a hypothetical acid such as HA. And let's write this reaction with water. We know that the acid will donate a proton, so what's going to happen is that this H positive from the acid will be donated to water. So when it donates its hydrogen to water, the leftover part will be A minus. Okay. So now because acid has donated the proton, so therefore it is an acid, and because water accepted the proton, so it's a proton acceptor, so therefore water is a base in this case. Okay, so let's pay attention to the leftover part after donating after donating the proton. The leftover part is A minus. So this is the leftover part. The leftover part of an acid is known as conjugate base. Similarly, the leftover part of water, after it accepts a proton, it will be H3O positive. So it's a hydronium ion, right? The leftover part of a base is known as conjugate acid. So together they are known as conjugate acid base pair. So remember, the acid, when it donates the proton, whatever is the leftover part is known as conjugate base. And for a base, after it accepts the proton, such as here, the leftover part is known as conjugate acid. So let's take a look at a real reaction. So in this case, our acid is acetic acid. It's the acid which is found in vinegar, and the base is still water. So after the acetic acid donates this proton, the leftover part is the acetate ion. As you can see, it does not have that proton anymore because it has donated it to the water. And water, after accepting the proton, now it has one extra proton, so therefore water is a base because it has accepted it. So hydronium ion is the conjugate acid of water, and the acetate ion is the conjugate base of acetic acid. Now why the acid gives a conjugate base in the other side? The reason is, if you look at it in forward direction, the acid is donating the proton to water, acetic acid. But if we look at the reverse reaction, in the reverse reaction, the hydronium will donate its proton back to the acetate ion, and we will get our reverse or acetic acid back. So in the reverse order, acetate ion will accept the proton. So that's why acetate ion is known as a base, and it's called a conjugate base. In any case, just remember that any acid, after it donates a proton, whatever is the leftover part, so that leftover part is known as a conjugate base of that acid. So together they are known as conjugate acid base pair. The structure and formula of conjugate base can be easily determined from the starting acid with this easy exercise. So take your starting acid. For example, if we have HCl and we want to determine what will be its conjugate base, so all we need to do is start with the formula and charge of the acid, which we have it here, and then decrease the number of hydrogen atoms by 1. So in our case, we have only one hydrogen. So if we decrease by 1, so we'll be 0. So therefore on the other side, we'll have just Cl because we have one less hydrogen. And then finally, decrease the charge by 1. So on the starting acid, we have no charge. So its charge is 0 because it's a neutral molecule. So if we decrease by 1, so therefore the charge will be -1. So our conjugate base of HCl is Cl -1. Similarly, if we start with a acid who is not neutral, for example, if we start with H2PO4 negative, and that's our starting acid, and we want to determine its conjugate base. So we'll do the same exercise. First we will decrease the hydrogen by 1, and then we'll decrease the charge by 1. So our hydrogens are 2 on this side, so if we decrease it, so we'll have 1 hydrogen, so it will be HPO4. Charge is -1, so we're gonna decrease by 1 more, so charge will become -2. So conjugate base of H2PO4 will be HPO4 2 negative. So this will be the conjugate base of this acid. Similar exercise can be done to calculate the structure and formula of a conjugate acid if we start with a base. For example, if we have HCO3, that's a bicarbonate, that's our base, and we want to determine what will be its conjugate acid on the other side after it accepts a proton. So to determine the formula and and the charge of conjugate acid from this starting base, all we need to do is add 1 more hydrogen and add +1 charge. So in the starting base we have 1 hydrogen, so in its conjugate acid part we will have 2 hydrogen, so it will be H2CO3, and its starting charge is -1, so that's -1, and we will need to add 1 more, so on the other side the charge will be neutral, so it will be H2CO3. So that will be the conjugate acid if we start with this conjugate base. Let's label the conjugate acid base pairs. Remember, in Bronsted and Lowry definition, the substance which donates the proton is a acid. So in this example A, H2SO4 is donating the proton, and after it donates the proton, so that is the leftover part. So because it's a proton donor, so therefore H2SO4 is acid and HSO4 is the conjugate base. Now on the other hand, water is accepting the proton, so therefore water is a base and H3O4 is the conjugate acid. So these two are the acid-base conjugate pairs. In example B, the proton donor in this case is water. So therefore water will be an acid because it's donating the proton, and leftover part after donating the proton is hydroxide ion, so therefore water will be an acid and hydroxide ion will be the conjugate base. On the other hand, the hydrogen carbonate ion, it's accepting the proton, so that's the proton acceptor, so therefore it's a base, and the carbonic acid, so this is carbonic acid, so this will be the conjugate acid. In example C, the proton donor is Hi, so it will be an acid. Proton acceptor is water, so water is a base. Leftover part, excuse me, is the iodide ion, so iodide ion is the conjugate base. and for water the leftover part is hydronium ion, so hydronium ion will be conjugate acid. Strength of an acid is measured by the extent to which the acid donates a proton to form hydronium ions in water. For example, in this case, an equation for dissociation of HCl is in water is shown, and we can see here that HCl donates a proton to water and it forms hydronium ion as well as its conjugate base. Strong acids are those acids which dissociate in water completely. So the meaning is that if you have, uh, for example, 100 molecules of HCl in water, all 100 molecules will dissociate or will donate their proton to water, all of them. So those acids which dissociate completely or which donate their protons completely to water and form hydronium ions, they are known as strong acids. HCl is the only strong acid produced in human body, and it performs the function of food digestion. Strong acids are highly corrosive when concentrated, but they are safe to handle as dilute solutions. This table shows the names and formulas of 6 common strong acids. Just like strong acids, strong bases are also those substances which completely dissociate in aqueous solutions and produce hydroxide ions. For example, sodium hydroxide is a strong base, and in water it dissociates completely, 100% dissociation, and resulting product is a hydroxide ion and a metal cation. Ionic compounds composed of hydroxide ions and group 1A and 2A metal ions form strong bases. Strong bases are also highly corrosive when concentrated, but they can be handled safely as dilute solutions. Examples of common strong bases are shown in this table. All of these examples are ionic compounds between group 1A or 2A metals and hydroxide ion. Let's identify strong bases from this list. As we learned that ionic compounds made up of group 1A metals or group 2A metals and hydroxide ions are strong bases. So therefore, we can say that calcium hydroxide is a strong base, sodium hydroxide is a strong base, and barium hydroxide is also a strong base. Sodium is from group 1A, so that's why it's a strong base, and it both calcium and barium, they both are group 2A metals, and we know that ionic compounds made up of group 1A or 2A metal with hydroxide ions are strong bases. So all of these three are examples of strong bases. Opposite to strong acids and strong bases, weak acids and weak bases are characterized by little dissociation in water. They produce very few ions in aqueous solutions and are weak electrolytes. The reaction of a weak acid or a base with water is reversible, and therefore the two half-headed arrows pointing in the opposite direction are used in the chemical equation. For a weak acid or a base at equilibrium, the concentration of reactant is much greater than the concentration of products. So that means at any point at equilibrium, most of the reactant is not dissociated. Only very few molecules will dissociate. So therefore, the quantity or the concentration of product is low. So because the ions are low, concentration, therefore they are weak electrolytes and they conduct a small amount of electricity. As we learned in previous chapter, that if an electrolyte dissociates completely, it would produce large number of ions and it will conduct um, a large quantity of electric charge, and hence this bulb will glow brightly. So this kind of um, solution or this kind of electrolyte is known as strong electrolyte. Weak acids and weak bases are, on the other hand, are weak electrolytes. And the molecules which do not dissociate at all, those are called non-electrolytes. Organic acids such as acetic acid and citric acids are most common examples of weak acids. Acetic acid is found in vinegar, and the citric acids are found in all citrus fruit juice such as lemon juice, orange juice, etc. Inorganic acids such as carbonic acid, phosphoric acid, and hydrofluoric acids are also examples of weak acids. Common organic weak bases include nitrogen with non-bonding electron pair and with nitrogen and carbon bond. Common inorganic bases include uh, hydrogen carbonate ion, it's also known as bicarbonate, and carbonate ion. Ammonia is also a weak base, as we saw earlier in this chapter. In chapter number 6, we learned that Le Chatelier's principle allows us to predict how a reversible reaction at equilibrium responds to a disturbance. The reaction shifts in the direction that counteracts the disturbance. A shift to the right means an increase in the rate of forward direction, and a shift to the left means an increase in the rate of reverse reaction until the equilibrium is attained. Le Chatelier's principle can also be applied to a change in the concentration of one of the reactants or products in reversible reactions of weak acids or weak bases in aqueous solution. Consider, for example, the reaction of carbonic acid in water as shown by this equation. At equilibrium, the concentration of reactants and the concentration of products is constant. If additional hydronium ions are added, so that means that we are creating a disturbance on the product side because we are adding more hydronium ions. So therefore, Le Chatelier's principle predicts that the reaction will now shift to the left to consume the added hydronium ions. So if we add more hydronium ion or anything in the product side, equilibrium will shift to the opposite side or shift to the reactant side. In this shift to the left side, hydronium ions and hydrogen carbonate they will react more and they will produce more carbonic acid because now the reaction is favoring the backward or reverse direction or left direction. In biochemical pathways, reactions are approaching equilibrium, which means that they are continually adjusting to disturbances, particularly the concentration of hydronium ions, which naturally fluctuate as a part of metabolism. Let's take a look at this problem. Ammonia is a weak base. Write the equilibrium reaction for ammonia in aqueous solution. So ammonia with water, because it's a weak base, so therefore it will be a reversible reaction. because ammonia is a base, it will accept a proton. So after accepting a proton, it will become NH4 with a positive charge, and because water donated a proton, so it will become OH negative. So this will be the equilibrium reaction for ammonia in aqueous solution. Part B is, if additional hydroxide ions are added, will the reaction shift to the left or right? So if we add additional OH, now OH is in the product side, so therefore additional OH means that we are creating disturbance on the product side. So therefore, because we are creating disturbance on the product side, according to Le Chatelier's principle, the reaction will shift to the opposite side, which will mean that it will shift to the left side. So that's part B. Equilibrium will shift to the left. Part C is, if some ammonia molecules are removed, will the reaction shift to the left or right? So ammonia are removed. So ammonia are removed means that now we have a lack of ammonia on the left hand side. So because we removed ammonia, so because a void is created, so now again we have created a negative disturbance. So when we add additional OH, we create a positive disturbance because we are adding more. So you can consider this disturbance like a pressure. So if you add more on this side, so it will push everything on the other side. But if you remove something, so now you have created a vacuum. So it again means that the reaction will shift to the left to occupy that lack of material which was removed. So lack of ammonia means again equilibrium will be shifted to the left side.